So the red bar keeps going down. We are about halfway. And the topic of today is the leptonic standard model. It's not a formal name known to the wide community. It's the name that Yuval and I gave to this model that we will discuss now. But let me just repeat. So we started with introducing the rules of how we construct Lagrangians. We saw that under our rules, the list of allowed terms is very limited. Purely scalar terms can have quadratic, trilinear, or quartic terms in the scalars. In addition, there is always kinetic term with derivative, because the first thing we want to describe is free propagation in space-time, and that's what the kinetic terms allow us to do. The terms made out of purely fermions can have only two fermions in their normalizable Lagrangian, either Majorana masses or Dirac masses or both. Terms involving both scalars and fermions have two fermions and a single scalar, and that's the Yukawa terms. That's the full possible list of terms made out of scalar fields and fermion fields. So it's a very limited list, short list. And then when we impose symmetries, then some of these terms are forbidden. Some of the coefficients of these terms might be related by the symmetry to each other. And so it's more and more constrained. Lagrangian, in a sense, becomes simpler and simpler as we impose bigger symmetries. And then we discussed abelian symmetries. And the main thing to take from that is that when we impose a local abelian symmetry, we are forced to introduce into the model a gauge boson, a spin-1 field, massless, no self-interaction, so it's neutral. It doesn't transform under its own U1. And QED with the photon was an example of that. Then we introduced non-abelian symmetries, and these operate on like vector of several fields, but if there is a symmetry, we cannot distinguish which field is filled in an experiment. They are all the same. And the main message to take from that part was that if we impose a local non-abelian symmetry, then we must again force to introduce a vector boson field, spin-1, in the joint representation of size n squared minus 1 for an SUN symmetry. So for SU2, a triplet, for SU3, an octet, etc. And that field is massless and does have self-interaction. It does transform under its own symmetry. Then we went to spontaneous symmetry breaking, and which is the case when the ground state of the universe does not share the same symmetries as those of the Lagrangian. Or if you want, there is a degenerate state of ground states, of vacua, and the universe has to choose one. Whatever it chooses, it's the same physics among these degenerate vacua. This is a consequence of the symmetry. But sitting in a specific ground state or vacuum means that the symmetry is broken, and we call it spontaneously broken. And the main lesson from that is that all the transformations by a generator that are broken, now the related gauge bosons acquire a mass, and each of them, sorry, I'm losing my voice, just a minute. I'll recover, don't worry. So for each generator, there is a corresponding member of the joint representation, if you want, and this member gets a mess if the transformation related to it is broken, and it, what we call it's the would-be Goldstone boson, one of the scalars in the multiplet that got the vacuum expectation value that broke the symmetry. A lot of words. We will demonstrate this in the leptonic standard model. So we will go through the process that I said what model building is for me. We start by defining the model. Defining the model means we'll say which symmetries we impose on it and what is the scalar content and the fermionic content of the model. From that, we will construct the most general renormalizable Lagrangian that is consistent or that is made out of the fields that we introduced and consistent with the symmetry that we imposed. So that's the building of the model part. From that Lagrangian, we will understand which phenomenology, which nature, if you want, it describes. What are the elementary particles of nature? So what are they massive or not? What are the quantum numbers under the symmetry of nature? That's the spectrum. Then we will extract the interactions of these, mainly usually of the fermions, what we call matter particles. What kind of interactions they have. Does the model have accidental symmetries? Symmetries that we did not impose but come out of the symmetries that we did impose, the particle content and renormalizability. And there will be here interesting accidental symmetries. How many parameters does the model have, which tell us how many experiments we have to do to fix the values of these parameters, and when do we start to test it. And I'm not sure I will go into that low energy test. Okay, it has a purpose of why low energy, what I mean here. So that's the program. This is a long chapter, if you want, compared to all other. So we will not have, I think, 2 red bars this morning, just this one. And if we finish in the morning this, then in the afternoon, we will go to the standard model, which is where we aim. This is pretty close to the standard model. So first of all, it's interesting because it incorporates the 3 aspects that we went over during the previous lecture. The model has in it an imposed abelian symmetry, it has an imposed non-abelian symmetry, and it has spontaneous symmetry breaking. So we'll see how all of these combine in one model. Second, perhaps more important, it's relevant to nature. It describes the interactions of the leptons. The leptons are the charged leptons, electron, muon, and tau, and the 3 neutrino types. It describes them. The interactions that they have in nature that we are aware of are the weak interactions, the electromagnetic interactions, and the Yukawa interactions, and the model has all 3. And finally, it's a big part of the standard model. Much of what we will see happening in the leptonic standard model directly applies in the standard model. What is missing in the leptonic standard model compared to the standard model is quarks and strong interactions. So we'll see in the definition of the standard model what is added and how that adds the quarks and the strong interactions compared to the leptonic standard model. So, by the way, leptons, the definition of what leptons are, is exactly fermions that are not sensitive to the strong interactions. That's why when we discuss only leptons and not quarks, we are not worried about strong interactions. Okay, so what I like about the definitions of all these models, including the standard model, is that essentially it's usually a 3 or 4 line definition. And the fact that from these 3 or 4 lines come out, I don't know how many predictions, definitely thousands of experimental tests, it impresses me. I hope it impresses you. I mean, this is a very simple starting point. Simple, not in the sense that mathematics is simple, but the definition is very short and basic. So, we impose a symmetry, a local SU2 cross U1. Non-abelian factor and an abelian factor, and we give them names for this particular model. SU2 L for left, for reasons that we will see, and U1 Y, which stands for hypercharge. I don't know why the letter Y stands for hypercharge, but that's the jargon of the community. But anyway, mathematically, it's imposing local SU2 cross U1. The fermion content, that's also something that has to be in the definition. The fermions come in two types of representation. There are left-handed fermion fields in the doublet representation of SU2. And carrying hypercharge, this Y equals -1/2. And there are right-handed fermions that are singlets of SU2, so they do not transform under the SU2 transformation. They remain invariant, they are singlets, and carry hypercharge -1. So these two types of representation, there are 3 copies of each in the model. 3 L left, L1, L2, L3, and 3 E right. E right 1, E right 2, E right 3. Why 3? Because that's what nature has. And actually, I think nowadays, for a time we thought we understand why there should be 3 and no less. I think nowadays we do not understand why there are 3. We thought that there should be 3 generations, okay, then in the standard model, because that's a necessary condition for CP violation. And we know that in the universe, the symmetry CP between particles and antiparticles is violated in order that antimatter will disappear and matter will survive, which is the situation in the universe. However, in the meantime, we discovered that the CP violation of the standard model, I'll come to that back later, is completely irrelevant to this cosmological observable, the baryon asymmetry. It contributes to it at least 8 or 9 orders of magnitude below its value. It's a tiny contribution. And so it could be that the standard model would have been 1 generation or 2 generations, yet we do not understand why nature chooses to repeat this 3 times. Nature seems to have been the same, almost, not exactly the same, but close to what it is, also with just 1 copy, but that's nature still to be understood. Or perhaps our thinking that nature should be economical, should have the minimal number of things in order to reach the universe that we live in. Maybe nature does not have economy in its considerations and it does what it wants. We don't know. Okay, so yes.
Minimal number of generations to give CP violation is 3.
Yes.
That's economical, yes,
but not in the lepton sector. This will
Yes,
come out in the standard
but
model.
if we want to ask the question, what is the strongest hint towards 3 generations? Would not this Z decay width to invisible particles that tells
Which?
that Z decay width to invisible particles, this neutrinos, tells us that there are 3 generations of neutrinos, right?
Well, we know that there are 3 generations because we know that there is electron, muon, and tau, for example. So we know that there are 3 generations.
We know that there are 3.
But I'm saying that if we had only electrons, up quarks, down quarks in the universe, so let's say electrons, protons, and neutrons, then the universe would be very much as it is now, in the absence of these other small differences. But we could still be here with just 1 generation. So, yeah. The scalar content, we introduced, the standard model has a single scalar field, a field related to spin 0 particle. It transforms a doublet under SU2 and carries hypercharge plus a half. Okay, just a reminder, it's here still written how a doublet transforms under an SU2 transformation, e to the I/2, tau b, theta b, phi, where tau are the three Pauli matrices, 2 by 2 matrices. A singlet goes to itself. It doesn't transform under SU2 transformation because it's a singlet. And the final ingredient in the definition is that this symmetry is spontaneously broken. The vacuum state has a smaller symmetry, only a U1 symmetry, and that we call U1 electromagnetism for reasons that will become clear at the end of this chapter. And so doing this tells us that there must have been scalars in the theory. We cannot have spontaneous symmetry breaking if we don't have scalars in the theory. And it tells us, in a sense, that mu squared is negative. Okay, so I could say instead of this, just have the scalar and mu squared negative, the same consequences. But what we aim in this model is really to have U1 electromagnetism, one of the things that symmetry that is not spontaneously broken. Okay, so now there is what I call an automatic procedure. There is a very methodical way of going from this definition into writing the most general Lagrangian that is made of the fermion and scalar fields that we introduced in the definition and is subject to the SU2 cos U1 symmetry. So we now go into that. You don't have to follow the details of, just to understand that what I'm doing, I think on this, on the next transparency, at least on 2, is completely dictated. I have no freedom up to something that, as I say. So having this symmetry and this content leads to a well-defined Lagrangian, as we will see. So first of all our Lagrangians have essentially 4 parts: kinetic terms, purely fermionic terms, purely scalar terms, and Yukawa terms. These are the 4 parts that are allowed in the most general Lagrangian. And we should find what's the most general renormalizable Lagrangian made out of these fermionic fields, doublet with hypercharge -0.5, singlet of SU2 with hypercharge -1, scalar field, this is a doublet of the SU2 and has hypercharge +0.5, and subject to this symmetry, local symmetry that I imposed. Now, this symmetry, SU2 cross U1, has 4 generators. 3 are related to the SU2 symmetry. SU2 symmetry has 3 generators, and they fulfill commutation relation, which is the algebra of SU2. Again, the technical details are less important. The commutation of 2 of the generators here, A and B and C, goes from 1 to 3, is I epsilon ABC, the antisymmetric tensor. So epsilon 1 to 3 is 1. Each time you permute 2 of the indices, it reverses the sign. And if you have 2 or more identical indices, this is 0. So it's a list of known numbers. And the generators of SU2 commute with the generator of U1, the hypercharge generator, because they belong to different groups. And here is the important step. We imposed SU2 cos U1, a local symmetry. So we must introduce vector boson field in the adjoint representation of SU2. I will call this W mu A, mu for the vector index, A for the SU2 index. So A is 1, 2, 3. It's a triplet, the adjoint representation, n squared minus 1, SU2, n equals 2, 2 squared minus 1 is 3. And it carries hypercharge 0. And a gauge boson that we must introduce to allow the U1 symmetry. And it's a singlet of the SU2 and carries hypercharge 0. So this is forced on us. If we want this symmetry, a local symmetry, symmetry has 4 generators, we must introduce 4 gauge bosons for the non-abelian part in the adjoint representation, for the abelian part, a singlet of all the symmetry group. Okay, so imposing this tells us there are 4 gauge bosons in nature. This is still a list of things that are inescapable. They come from the requirement of a symmetry. So for each of the gauge fields, we define a field strength, which is this thing. So W mu ni A is d mu W nu A minus d nu W mu A minus G epsilon ABC W mu B W nu C. So for example, W mu nu 1 is d mu W nu 1 minus d nu W mu 1 minus G epsilon 1 to 3 W 2 mu W 3 mu, more or less. Here, this thing is the only freedom in this process. It's a dimensionless parameter, G, and in order to know what it is, we need an experiment. So this introduces one parameter to the theory, which value is not predicted, and it's called the SU2 coupling constant. Then when we have to replace for the local symmetry the space-time derivative with a covariant derivative, and the covariant derivative looks like that. The space-time derivative necessary to keep this possibility to describe free propagation in space-time, IGW mu A TA, where TA is a matrix which depends on the size of the multiplet or the field of which it acts. Here, for SU2, all the field content was either doublets or singlets. For singlets, TA is 0. Remember, their transformation is e to the I WA TA times theta, and if we want this e to the power of this more or less not to change, then what's in the exponent has to be 0. So for singlets, TA equals 0. For doublets, TA are these Pauli matrices, 2 by 2 matrices, the 3 of them. And IG prime, an additional parameter that we introduce into the theory, that we have the freedom to introduce, and that we call the U1 coupling constant, B mu, times the charge under the U1y, which depends again on the charge of the field in which it acts. So, for the doublets, TA equals half the Pauli matrix. For the singlet, TA equals 0. And phi is in the doublet with hypercharge plus half. So the covariant derivative acting on this is d mu. Since it's a doublet, it has this combination. Since it has hypercharge plus half, it's here plus I over 2. For these left-handed fermion fields, they are again doublets, so they have this term, and they carry hypercharge minus a half, so it's minus I over 2, this combination. The E right are singlets of SU2, so for them TA is 0, so we don't have a term with the W in the covariant derivative, and they carry hypercharge minus 1. Again, the details are less important. What is important is this, that what is the field strength and what is the covariant derivative is entirely dictated by the symmetry, except for 2 parameters, G and G prime, that have to be fixed by the experiment. Everything else, all the mathematical form here, is dictated by the symmetry. No freedom. So, we start with the first 3 parts that I will leave for the next transparency. We are now constructing the Lagrangian. Kinetic terms for all the fields. Kinetic term for the W. Again, let me go back. This W mu nu A is written here explicitly. So that's what it is when it's written here. A kinetic term for the B field. And again, this B mu nu is written here. The form is entirely dictated. And d mu phi dagger d mu phi, a kinetic term for the fermionic left-handed fields, a kinetic term for the right-handed fermions, where the covariant derivative that appear here is again written in these 3. So the kinetic term in particular is completely dictated up to G and G prime, which are parameters. Now, L left carries hypercharge minus half, The E right, the three of them carry hypercharge -1. So all of these fermionic fields are charged, cannot have Majorana mass terms. The left-handed fields are doublets of SU2. The right-handed fields are singlet of SU2. So there is no matching pair. There is no pair where the left-handed field and the right-handed field transforms in the same way. That is what I call a chiral representation, and it forbids Dirac mass terms. So we do not have mass terms for the fermions in this model. L psi is 0. Neither Majorana nor Dirac, because fermions are charged and chiral. Yes?
Can you write the beta term for W mu mu? So it is non-abelian. Beta term means epsilon mu mu rho sigma.
What is W mu nu?
It is a
You mean
non-abelian gauge.
it's this. W mu nu A is here.
For SU3, you can write the epsilon mu mu rho sigma G mu mu.
Okay, no, so I said I will ignore the terms with the epsilon. The one consequence they have relevant to phenomenology is the electric dipole moment of the neutron for the SU3. So it's a non-perturbative effect. I will do in this course only perturbative effects. Okay, it's a non-perturbative, complicated physics of little relevance to what I will describe. Okay, so I will not write these terms. And finally, for Yukawa theorem, we have a single scalar transformed like a doublet of hypercharge plus half. So we must ask, is there any combination L left and L left, or E right and E right, or L left bar and E right, that transforms also as a doublet with hypercharge plus or minus a half, because then we can combine it with the scalar in order to get a Yukawa term that is invariant under the symmetry, and indeed there is such a combination. Any of the L left bar and any of the E right bar, any such combination transforms as a doublet with hypercharge minus a half, so it can be combined with the scalar field, which is also a doublet with hypercharge plus half. So we have here, if you want, under SU2, a doublet, a singlet, and a doublet. This combination has in it a singlet, so it's legit, it's a legal one. And the sum of hypercharges is plus half, minus 1, plus half, which is 0, which is another condition that we are able. So yes, we have Yukawa terms. We have 9 Yukawa terms, okay? Because for each of the I, there are 3 copies, I equals 1, 2, 3. This of the J, this transforms as this under the imposed symmetry. So all 9 combinations are allowed. So these are the 3 parts: the kinetic, completely dictated, psi, L psi 0, L Yukawa. These combinations are there. Everything which is allowed, we are writing. What about L5? So, again, it's very similar to the things that we've done with previous models when we discuss spontaneous symmetry breaking. So this is the scalar potential minus mu squared phi dagger phi minus lambda phi dagger phi squared. This form repeats itself. Lambda must be larger than 0, and because we said we want spontaneous breaking, then we choose mu squared smaller than 0. We define v squared as minus mu squared over lambda. V squared is the value of v squared, unlike mu squared, which is not the value of mu squared. And we can rewrite this Lagrangian, replacing mu squared by v, and up to a constant term, which is not important for us, it will be written in this way, which tells us that phi dagger phi should have a vacuum expectation value of v squared over 2. That's the minimum. Now we have to choose a direction. That's the spontaneous symmetry breaking. Phi is a doublet. It has 2 components. If you want, T3 equals plus half and T3 equals minus half. Each of these is a complex component in the field. And we choose, first of all, where to put it, up or in the T3 plus half or minus half. And the convention is to put it in the T3 equals minus a half. And again, this is complex, and we choose to put it real, not an imaginary part. Any other choice would give the same physics. Okay? This is the conventional thing, but the symmetry tells us that any other choice would give the same physics. And indeed, such a vacuum expectation value breaks an SU2 cross U1 symmetry into a U1 symmetry. It still remains that I will show you that the remaining U1 is indeed corresponds to the U1 electromagnetism, the one that we imposed when we discussed QED. So it's not trivial that the symmetry that remains is the one that gives us the right properties under QED of the particles that we introduced. I am telling you, but I'll show it later, that the generator or the charge under this U1 is a combination of a generator of the SU2 with the U1 generator, and this combination is T3 plus Y. And perhaps I'll make this point now. It's some of you, I think, so this vacuum expectation value will not break generators. Okay. If I have some e to the I, call it x, this is now a gauge transformation acting on the absolute value of phi, and this equals phi, it means that the vacuum is invariant under this transformation. So if that's the case, then this part of the symmetry that fulfills that is not broken. Okay? So in order that that will happen, what is needed that x acting on phi will be 0. Right? Or if you want, I think it's clear that if x acting on the vacuum is 0, if the generator, if you want, annihilates the vacuum, then the vacuum is invariant under the corresponding transformation. So let's see. Let's take from here, what does T3 do to the vacuum? T3 is half of sigma 3 for a doublet. Still with me? I hope. And sigma 3 is 1 minus 1, so this is plus half, minus half, 0, and 0. Y for the scalar is plus half, which means that when we operate it on the doublet, it's really a unit matrix, plus half, 0, 0. Now we do T3 plus Y acting on 0 and V over square root of 2. This plus that. Sorry. Yeah. So we have 1 and 0, 0, 0. That's the sum of these two, acting on 0 and V over square root of 2. And this is 0. It annihilates the vacuum. So e to the I T3 plus Y times theta of x acting on 0 V over square root of 2 is 0 V over square root of 2. So the vacuum is symmetric under this combination, under this transformation. Right? The generators annihilated means that this particular transformation among all the transformations, so we can write that is e to the I T1 theta 1 and e to the I T2 theta 2 and e to the I T3 minus Y. These three combinations do not annihilate the vacuum. and therefore the vacuum breaks these 3 out of the 4 transformations. But the one with T3 plus Y annihilates the vacuum, and so it's an invariance of the vacuum. So in the vacuum, this part of the symmetry, one of combination of the 4 generations, survives as a symmetry. It's not broken. Okay, I hope this is... So that's how I know that the combination T3 plus Y is not broken. Had I chosen, for example, the vacuum expectation value to be in the upper component, what would have survived is T3 minus Y instead of T3 plus Y. But the physics would be the same. It would just give me a different definition of what the surviving symmetry is. And it remains for me to show you that this Q is the electromagnetic charge. So that will come later. But for now, what we see is that out of the 4 generations, 3, T1, T2, and T3 minus Y are all broken, spontaneously broken. They are not symmetries of the vacuum, but one combination survives, so there is a single U1. Okay. I will, for those that are interested, this complicated transparency is one that is related to something that I showed before, a trick of getting rid of the explicit appearance of the would-be Goldstone boson in the final Lagrangian, and the one that shows that 3 of the vector bosons get an additional component. The would-be Goldstone boson becomes the longitudinal. So I will not repeat it. I think it's too complicated, and it's not a principle now. What I'm saying is that there is a gauge where the fields phi has just 1 degree of freedom instead of 4. Originally, it's a doublet, and each of these is complex. So there is, if you want, phi 1 plus I phi 2, phi 3 plus I phi 4, and this phi 1, phi 2, and phi 4 disappear now from the Lagrangian with this choice, and there is only the real part of the lower component, and V is the vacuum expectation value, and H is the remaining scalar field, which has vacuum expectation value 0 in this way. So in the unitary gauge, we see that what will remain after the spontaneous symmetry breaking as the scalar content is 1 real scalar. The other 3 scalar would have been a Goldstone boson if the symmetry were global. They become the longitudinal component of 3 gauge bosons that acquire mass as a result from the symmetry breaking. There are 3 generators, T1, T2, and T3 minus Y, that are broken. It means that there are 3 gauge bosons that become massive vector boson, W1, W2, and a combination of W3 and B. We'll see that in a minute, but for the scalar content, all we have is a single real scalar field. This is, before we go to that, so I'm just saying that from now on, I will use this for phi. But before we go on, this is the leptonic standard model Lagrangian. We saw what appears, what doesn't appear, kinetic term for all the fields, the SU2 gauge boson, the U1 gauge boson, the scalar field, the left-handed fermion doublets, the right-handed fermion singlets, doublets and singlets of SU2, the Yukawa terms involving the left and the right-handed fields, and the scalar potential. That's the Lagrangian. And now we can interpret what does it tell us about nature? What does it describe? What is the spectrum? What are the interactions? How many parameters it has? What are the accidental symmetries, etc. So that's what we are now going to explore one after the other, when this is our starting point for this exploration. So to understand the spectrum of scalars, something actually that more or less did before, but we go back to the scalar potential. This was it. from now on I said I write phi this, and in a particular gauge where everything that appears are the physical particles, so there is this age, and when you put this phi into this expression, phi dagger phi, you get a mass squared term for age, and this mh squared is 2 lambda v squared. That's, if you put that into here. So it's not a complicated exercise to see what is the quadratic term in age. Moreover, age is the T3 equals minus half of the doublet, and the doublet has y equals plus half, so it's Q. The charge under the remaining symmetry is 0. Minus a half plus a half is 0. So it's, I call it electromagnetic neutral. What I mean is that it carries Q equals 0. It carries T3 plus y equals 0. So I have one real scalar field that is neutral under the remaining symmetry and has this mass, and we identify this with the scalar that was discovered 2012 at the LHC, and has a mass of about 125 GeV. And what impresses me and should impress you is this error. So within very short time after the discovery, it became one of the elementary particles whose mass is known with the highest precision. It's not the champion of this, but this is 10 to the minus 3 accuracy. Okay, 1 per mil accuracy on the mass. And it's not an easy particle. It doesn't appear often at the LHC. There is a very small branching ratio, and yet they were able to close in on the mass very quickly. So that's the scalar spectrum. A single real scalar field, no charge, and mass of about 125 experimentally. So yeah, so it tells us, if you want, what is this lambda v squared. I'm telling you that v is 246 GeV more or less. I'll come back to this point in a minute. And so it tells us, if we know v, and we'll see how we know v, it tells us the value of lambda. Not a very small number. What is the spectrum of the spin 1 particles of this model? So we know, before we start the analysis, that we should get one massless gauge boson, because there is a remaining local U1 symmetry, this U1 T3 plus y, U1 Q, U1 electromagnetism, as we will see. So whatever we calculate, we must get one vector boson that is massless. That's, if you want, a prediction for what our calculation should get. And we should get 3 vector bosons that are massive, because 3 of the 4 independent transformation, the one by T1, the one by T2, and the one by T3 minus 1, they are all not invariances of the vacuum. They are all spontaneously broken. So 3 combinations of generators are broken. It means 3 massive vector bosons. So that's what our calculation should give. And we do an explicit calculation because we want to see the dependence of the masses on the parameters of the Lagrangian. And where do these vector bosons, how can we find their masses? They are hiding in the kinetic terms for the scalar. Right? I remind you that, first of all, the mass has to do with the scalar, because they have to be proportional somehow to the vacuum expectation value of the scalar. That's the parameter that breaks the symmetry. If v equals 0, there is no symmetry breaking and everything remains massless. So they must be proportional to v, which means it must involve terms that include phi. Second, for bosons, it's always mass squared terms. So there is some coefficient that is mass squared, and then 2 fields, right? That's mass square terms involve two fields. I don't know, WW or whatever you want to call it. Not three W's, not four. These are interactions. Mass square terms involve two fields. And so we need terms with two two spin one fields and no other field there. Okay, just these two. And we indeed have it only in the kinetic terms of the scalar. So the kinetic term for the scalar is d mu phi dagger d mu phi. And d mu has in it the gauge bosons because phi transforms under the symmetry. So d mu has in it W and the B, the three W's and the B. And we must replace phi by its vacuum expectation value because we don't want the scalar field to appear. We are not interested in the term at the moment in the terms where the scalar age appears. So we just replace phi with the vacuum expectation value. That's part of what is going on. And these things, so not the del mu, but the other two things here, acting on the vacuum expectation value, this part of d mu phi dagger d mu phi is the thing that will give us mass square terms. So that's where we find the vector bosons. So this is d mu phi, I wrote it before, and d mu acting on the vacuum expectation value. By the way, the partial derivative acting on the vacuum expectation value is 0. So it's not just that I ignore this, but v is the same. It's independent of the space-time coordinates. At some point, I asked myself, and it took some time to answer, why? And the answer is that we are looking at the minimum of the potential, and if v would have been space-time dependent, then d mu phi would not be 0, and that would add to the energy of that state. And so the minimum, really, the minimal energy state, the ground state, must have a vacuum expectation value that is constant in space-time. Otherwise, it will just raise the energy of that state. So the minimal energy is when phi is a constant of space-time. So this cancelled, and here I write explicitly the other thing acting on 0 and v. So there is sigma 1. So let's for example, sigma 3 W3, and sigma 3 is 1 minus 1. So you see here GW3 and minus GW3. And just one more example, W1 times sigma 1. Sigma 1 is 1 minus 1 in the off diagonal. So you see here the GW1, 1 on the, and W1 on the off diagonal. Sigma 2 gives me that. And B mu is just the unit matrix here. So I just replace this explicitly with the form of these matrices. I know the form of these matrices. And then I get this Lagrangian, or this part in the Lagrangian. Again, the details are unimportant, just that it's completely dictated. And finally, this is the result that I get. It appears also on the next slide, so I'll go there. So this is what we got. These are terms that are quadratic in the vector boson field, W1, W2, W3, and B, and have coefficients of dimension mass squared. Not surprisingly, it comes from V squared. It's related to the symmetry breaking. So what does this tell us? So here, if you want, is a simple way to understand what is the spectrum. We define something called theta wick, the wick mixing angle, for reasons that I'll explain in a minute. The definition is there are two free parameters, G prime and G, and what is important is the ratio G prime over G. I define this to be tangent theta wick. Okay, so it's a definition of what theta wick is. And that allows me, or that tells me to do the following thing. First of all, you see that here I have something complex times this complex conjugate. So I call these the complex conjugate states W plus and W minus. Each of these is a complex state, and they are complex conjugate. So each of these is complex, and they are complex conjugates of each other, these two things. And given this definition, these things here are accompanied by G and G prime, then, for example, under this definition, it means that sinus theta is G prime over the square root of G prime squared plus G squared. Okay, this is geometry, trigonometry. So these two combinations that appear here are, given this definition, are this combination of the W3 mu and the B mu. And when I do this replacement, this rather complicated expression becomes much simpler. It becomes G squared V squared over 4 W plus W minus plus G squared plus G prime squared V squared over 8 Z mu Z mu. The important thing is that you can see here that there are 3 combinations of the gauge bosons that become massive. W1 and W2 are in here. Both of them become massive. Actually, they get the same mass. And Z is one combination of the W3 and B mu, and the other combination doesn't appear here, which means that it's massless. Had I not found a massless, it would have meant that my calculation is wrong, because I know that there is a local U1 symmetry that is not spontaneously broken. So there must be one massless gauge boson, and I call it A because this will be the photon. While the other things, the Z and the complex W, are massive. Z is a real field, so it must carry no charge under the U1, because if it carried charge, it must have been complex. W is complex, which reflects the fact that it is charged under the remaining U1. So it's not by arbitrary decision that I call this W plus and W minus. When you do the T3 plus Y acting on this combination, you will see that T3 plus Y acting on W plus give W plus, and T3 plus Y acting on W minus, the W1 plus IW2 gives me minus W minus, and so they have eigenvalues under the remaining generator Q plus and minus 1, so they are charged under this U1 with charges plus 1 and minus 1. So what do I have here? I have a two complex conjugate fields W plus and W minus. Their mass squared is given by that. Their T3 are plus and minus 1 and 0, so their Q is plus and minus 1. There is the Z field that has a mass squared with this dependence on the parameters of the Lagrangian. Comes from T3 equals 0. It's the W3. And the B, both have T3 equals 0, Y equals 0, so no charge. And there is the A field that has no mass, massless, and again, no charge. So again, these are the masses that I found. As anticipated, 3 massive vector bosons, 1 massless. Its masslessness is just a consistency check of our calculation. The interpretation of what theta weak is a rotation angle between 2 bases. One, the basis where the gauge bosons have well-defined transformation properties under the full SU2 cross U1. That's W3, part of the triplet, and B. And the other is the mass eigenstates made out of these, which have only well-defined transformation property under the remaining U1Q. They don't have well-defined transformation properties. They mix. These come from 2 different presentations, but these are the mass eigenstates. And theta is the rotation between these 2 bases. One more thing about the vector boson spectrum. We said that we'll have spontaneous symmetry breaking. The number of parameters doesn't change, but there are many more terms that are allowed usually, which means that there are relations between the allowed terms. And the Oracle 1 relation is perhaps the most famous relation of this model. So We have here mw squared, we have here the expression for mz squared. So the ratio between them, mw squared over mz squared, is g squared over g squared plus g prime squared. And the interesting thing about this is that the left-hand side here is just a measurement of the spectrum. Tell me what the mass of the W and the Z boson are, I'll tell you what this part is. This is entirely coupling constants that will signify interactions. So this is measured by all kinds of processes that involve the W and the Z. So left-hand side spectrum, right-hand side interaction rates. This relation is often expressed in this way. This can be translated into mw squared over mz squared cosine squared theta, because this combination here is exactly cosine squared theta. So this combination should be 1. So if we knew what sinus squared theta is, then we could have, and mw and mz, we could have tested this. But for now, what we'll do is the opposite. We'll assume this should apply and get from the spectrum the value of cosine squared theta or sinus squared theta, and this is what it gets. And later I'll show you how we get it from various processes, and we'll see whether it's consistent or not. Done with the scalar spectrum and the vector boson spectrum. What are the fermions of the theory? So they had no Dirac or Majorana mass terms in our original Lagrangian, but we said that even in this case, spontaneous breaking and Yukawa terms can give us masses to fermions after spontaneous symmetry breaking. So we had these Yukawas. Now I give names to the components of these left-handed doublets. In a sense, there was little, except to saying that one of them is T3 plus half and the other is T3 minus half. If the symmetry were not broken, there is not much significance to giving them names, because there is no way, if the symmetry is unbroken, of distinguishing experimentally whether what takes part is the upper component or the lower component. But the SU2 is broken. So now it does become possible to distinguish these two components. So it makes sense to give them different names. I call the upper component neutrino and the lower component charged leptons, so if you want Ni and E. And the right-handed, I also change the name because it's convenient. So I replace Erij with little Erij. In a minute, I'll give them even more explicit name. So I now, to get masses for the fermions, I again have to replace or to put, instead of phi, its vacuum expectantial value. And I get these 9 allowed terms. So I have a 3 by 3 matrix for the leptons, and it involves only the lower component, because here it's only the lower component that appears. So when I multiply L bar with this, the upper component does not play a role. Ni does not appear in the result, only the lower component that I called E left I. So it's a mass matrix between the lower component, the T3 equals minus half members of the lepton doublets, and the right-handed fields. Again, I said several times, I say how we do it. We can now change to a basis where this mass matrix is real and diagonal. I showed how it is done, so I will now not repeat it. So I move to that basis, and in that basis, real and diagonal, I give the 3 entries names, YE, Y mu, and Y tau, with the convention that YT is the tau is the biggest and YE is the smallest. And in this basis, I also give names to the neutrinos that are within the doublets of the charged lepton mass eigenstates. Okay, so these are the SU2 partners of the charged lepton mass eigenstate. So it's a special basis. It's the basis, the mass basis for the lower component, and I call the upper component of E. So the lower component I call E, or mu, or tau, and the corresponding neutrinos, Ni E, Ni mu, and Ni tau. So these names make sense only in the mass basis for the charged leptons, and I call the right-handed ones E right, mu right, and tau right, the right-handed ones in this basis, and what I get is this mass terms for the charged leptons. Each of them is the corresponding entry here, the corresponding Yukawa coupling in the mass basis for the charged leptons, times V over square root of 2, and there is E left bar E right, mu left bar mu right, tau left bar tau right, with the corresponding Yukawa, YE, Y mu, and Y tau. So I have three massive charged leptons, and since these are not Majorana mass terms, they are massive Dirac fermions, and their masses are proportional to the corresponding Yukawa couplings. And we already gave their masses when we discussed QED, but we know these three masses. And they must have well-defined transformation properties under the remaining U1. And moreover, since it's left bar and right, they must be in a vectorial representation of the remaining U1. So they must carry the same charge. And indeed, the left-handed component has T3 equals minus a half and Y equals minus a half. So Q is minus 1. And the right-hand component had T3 equals 0. It was a singlet of SU2. And Y equals minus 1 by the definition. So also Q equals minus 1. So it works. Our calculation is right. There are no mass terms for Ni, Ni mu, and Ni tau. So these are massless Weil fermions. A Dirac fermion has 4 components, a Weil fermion has 2. So M Ni equals 0. Their T3 is plus half, their Y is minus a half, so they are neutral under the U1 Q. Thank you. Wow, okay. Thank you very much. This is cocoa water? Yeah, okay. I'm tempted, but I'll do it at the end of my lecture. So we have 3 charged fermions that are Dirac fermions and massive, and 3 massless neutral fermions, which are the neutrinos. So all leptons are all the fermion fields that I introduced. All of them are in a chiral representation of SE2 cross U1. But the charged leptons are in a vectorial representation of U1, which allow them to get Dirac masses. The neutrinos are neutral under the remaining U1, so a priori they could get Majorana masses. But they did not. That has to do with the particle content of the model. So I will not go into this. I'll just say that we will soon find that there is an accidental symmetry under which the neutrinos are charged, and that explains why they do not get masses in this model. So the prediction of the leptonic standard model is that the neutrinos are massless, and experiments proved that this prediction is wrong, which makes us all happy, and build huge experiment to explore further neutrino properties. Now we have, but it's not within this model. In this model, they are just massless, and hopefully we will have the chance to get to the chapter of neutrino masses and see how is the thinking of the community going on based on the fact, on the experimental fact, that they are massive in contradiction to the prediction of the leptonic standard model and actually also of the standard model. So this is the answer of what is the spectrum of this model. We have, if you want, 4 spin 1 degrees of freedom, W plus W minus with charge. Charge is under this remaining U1Q, plus and minus 1, and their mass is GV over 2. A real vector boson of spin 1, charge 0, and that's its mass. What will become familiar as the photon field, spin 1, neutral, massless. We have a single spin 0 particle, a real scalar, that is neutral under the remaining U1 and has this mass. 3 charged leptons, spin half, carrying charge -1, and masses proportional to the Yukawa couplings. 3 neutrinos, spin half, charge 0, massless. This is the spectrum. So that's the first thing about that we wanted to explore after we have the Lagrangian. Second interaction, yes.
Can you please go back that from where that mass zero term for the neutrinos it's coming from this model? Can you go back to that? In this model,
So-
where is that coming from?
Okay, so all we have is these Yukawa terms, and now we put explicitly here neutrino in the upper component and charged lepton in the lower, and this is the vacuum expectation value. And so now is the I have here now the left bar, 0, b over square root of 2, e right. And so now this times that, knee left multiplies the 0, and then for all of that there is some y, so there is y. This times that, it's okay. E left bar v over square root of 2, e right. So it just, you don't get knee left in the any mass terms for the knees, because that's what it gives. Later I'll give an argument based on symmetries why they do not get masses. Let me have it, okay, maybe I'll tell you this because in the end this is what happens. Suppose we had a field, I call it now n right, which is a complete singlet of SU2 cross U1, a complete singlet of SU2, n carries no charge. If I had such a field, I could write additional Yukawa terms. Then I could write, I call it now yn to distinguish it from this, L left bar, phi dagger, n right. So this is a doublet and this is a doublet. This is a singlet, so it's SU2, it's okay. And hypercharge, this is plus half, phi dagger is minus half, and R is 0, so it's also okay. So I could write such a term. Now, let's see what happens. So I have yn and knee left bar, e left bar. Phi dagger, okay, phi dagger, I should have it transposed. It means that the upper component now in this phi dagger is the one getting, okay, it's something called phi tilde. You have to replace v over square root of 2 and n right. So these Yukawa terms would have yn v over square root of 2, knee left bar, and right. So had we added such fields to our model, the neutrinos would become massive. So the simplest explanation of why they do not get masses is that we did not have fermion fields that are singlets of the entire imposed symmetry in our model. As long as we didn't know that neutrinos are massive, we had no reason to add these fields, so we did not add them. Now that we discovered, we have to extend the model, and most of the extensions do that. It's a little bit more complicated than that, because once you add this, then also Majorana mass terms for these fields are allowed because they are complete singlets, so they are not charged under anything. So from the beginning, you can get messes for them, and that makes this exercise a little bit more complicated. And if we get to the chapter on neutrino messes, we will do that exercise. Okay, so, but it's, yeah, so it's simple, but the simplest thing that we could do to give neutrino messes is to add such fields to our model. We didn't. Okay, so there is the definition of the model. And by that definition, the model, in this model, the neutrinos are massless. So what kind of interactions do we have? From the scalar potential, we have Higgs boson self-interactions. I'll skip that. There are three linear terms in the Higgs and quartic. There are Yukawa interaction. So these fermions have Yukawa interactions, and that's coming from L Yukawa. So two fermions and the Higgs particle, the Higgs boson. And the kinetic terms give a very rich set of interactions. There are those that are mediated by this A field, the massless A field. This I'll show is actually the QED interactions. This A field is the photon. There are interactions among fermions mediated by the Z boson, the heavier of the two. And this I'll call neutral current weak interactions, and are those that are mediated by the charge W plus and W minus, and they are called charge current weak interactions. So neutral and charge in correspondence that the mediator of these interactions is neutral under U1 electromagnetism, and charged because the mediator of these interactions is charged under U1. So, yeah, so the main thing I want is to talk of how these interactions, these three types, arise from the kinetic term. And I'll skip, I think, the Higgs for now. So this is the covariant derivative. It's general form in a theory with a local SU2 cross U1. And what is TA and what is Y depends on the specific field. But we moved from the basis of W1, W2, W3, and B to the mass basis for the vector boson, W plus, W minus, Z, and A. And so we would like, in order to understand which type of interactions these bosons mediate, I will now move from this basis to this basis, and in the language of W plus minus A and Z, just this basis transformation that gives me these combinations. So it's rewriting exactly this, moving from the basis of W1, 2, 3, and B to the basis of W plus, W minus, Z, and A. That's the exercise that has been done here. I skip the Higgs interactions and go to the interactions that involve A. So in that expression, d mu included in it a term with A, which was G sinus, this stands for sinus theta weak. Remind you, I defined tan theta weak to be G prime over G. So sinus is G prime over square root of G squared plus G prime squared. Plus G prime cosine theta weak Y, all of this A mu. So A mu, this is how it couples to the various fields. This set of coupling constant, this set of coupling constant. And a little miracle happened here, and it's the following. It's the fact that, if you want, the miracle is that GSW equals G prime CW. Actually, in retrospect, it shouldn't have been expected, but it's nice, I think, to see it concretely. So SW is exactly G prime over square root of G squared plus G prime squared. So this combination is that. And cosine theta weak is G over square root of G squared plus G prime squared. So G prime times cosine is also exactly the same combination. So we can combine them into this. And no wonder that A mu is related to the generator of the invariant of the U1 that remains, right? It's the massless gauge boson, and we know that this combination is the one that is not broken. So it should have come this way. It should have been proportional to T3 plus Y, that we called Q, and so it couples proportionally to Q, G prime over square root of G squared plus G prime squared. Now I will give a new name to G prime over square root of G prime squared plus G squared. I will call it E. And when I call this combination E, right, this is a combination of coupling constants, dimensionless. E is a dimensionless number, which is thus this combination. So all of this is replaced by E times Q. All that is written here. And so I replace it E times Q. I know that Q for the charged leptons is -1. And so this is the interactions of the photon with the charged leptons. I know that Q for the neutrinos is 0, so they do not interact with the photon. They are electromagnetically neutral. And this is exactly the Lagrangian that we had for QED. The photon couples with coupling constant E proportionally to the charge of the fermions with which it acts. So we get here the QED Lagrangian. And in this model, it comes from a larger symmetry group that is spontaneously broken into U1 electromagnetism. So if you want, this is the proof that indeed the massless vector boson is the photon and its directions are the QED interaction. It interacts with the 3 Dirac fermions of charge -1. And so QED is part of the leptonic standard model. I will do this methodically in all the interactions, say something about features of the interactions that come out of the definition of the model. So these qualitative features of the QED come from these 3 or 4 lines that I wrote in the slide that defined the leptonic standard model. Okay, I didn't do anything additional. I did not use any experimental information here. There was definition. I got the Lagrangian, and I got in the end that this is the QED Lagrangian. So first of all, the photon couples to the Dirac fermions, so it couples with the same coupling to the left-hand and right-hand fermions. So it's a vector-like coupling, same for left and right, and it's parity, charge conjugation, and CP conserving. Second, it's diagonal. A couples to E plus E minus, mu plus mu minus, tau plus 2 minus, but not to any of these combinations, which would have been allowed by a global U1 of the same type. But it's the local symmetry that forbids the photon to couple to this. Let me tell you for a minute a qualitative argument why gauge bosons of exact symmetries always couple diagonally, and perhaps also I should say first that it's also universal. It's the same coupling, just E, to all the fields with the same charge. So same coupling for E plus E minus, mu plus mu minus, tau plus tau minus. It's just E because the charge is defined as -1. So when we have a gauge boson, it's introduced in order to compensate for the non-invariance of the kinetic terms. And the kinetic terms are universal, okay? The kinetic term for the E and the mu and the tau, any fields here, they have the same coefficient in the canonical normalization, and they are diagonal. That's the canonical normalization. There are no off-diagonal terms in the kinetic terms, and all of them for the fermions have the same coefficient. So to compensate, so their non-invariance is exactly the same of this. It has to compensate for that, and the only way to do it is if it couples universally to all of these fields. So for fields of a given charge under a gauge symmetry, a gauge boson of exact symmetry couples to them in a universal way, which says no off-diagonal couplings and and the same coupling to each of them, because it comes in correspondence to the kinetic term of these fields. And the kinetic terms are universal. Okay, the Z-mediated interaction. So this was the combination that appeared in the covariant derivative before the Z. It's customary, there are many ways to write this combination, and the customary way to do it is G over cosine theta weak times T3 minus sinus squared theta weak times Q. For the left-handed charged leptons, T3 is minus a half, Q is minus 1, so that's what appears. For the right-handed charged leptons, T3 is 0, they came from singlets, and Q is still minus 1. And for the neutrinos, T3 is plus a half and Q is 0, so that's how it couples. So these interactions of the Z boson with the fermions in this model, there are three different sectors if you want, the left-handed charged leptons, the right-handed charged leptons, and the neutrinos. The couplings to each of these sectors is different, as we can see here. These are different coefficients. These interactions is what is called neutral current weak interactions. And now their features. Again, I emphasize that all of these qualitative features of the Z-mediated boson come from the definition of the model. Okay? We didn't do anything beyond following what the model tells us. So first of all, these are chiral. Unlike the photon, the left-handed and right-handed charged leptons are not the same. They are different from each other, which means immediately that it violates parity and charge conjugation. However, I did not explain it, but CP violation requires that there are complex couplings. All of these couplings are real, so it's CP conserving. It's still diagonal. Z couples to all these kind of combinations, but not, let's say, to E plus U minus, no to neutrinos of different types. I will not explain here why that arises, and it's still universal. Each of these have all three species, all three left, E left, U left, and tau left, have exactly the same coupling to the Z bosons. Unlike the photon is the gauge boson, is not a gauge boson of exact symmetry. Okay, there is no related symmetry now that the Z compensates. So, in general, there is no reason for these couplings to be universal. There is no argument like the one I gave before for the photon of why the Z couplings are universal. It's a special feature of the LSM and actually also of the standard model. I will not explain it now. I just say that when we extend the standard model, do any extension, we keep human electromagnetism as an exact symmetry. In all the extensions, the photon couplings are universal because it's a gauge boson. The Z couplings, it's the universality of the couplings depends on special features of the standard model. They are often do not hold in extensions of it. And so new physics could give off-diagonal Z couplings and could give couplings to E, mu, and tau that are different from each other. And so the search for non-universality of Z couplings is a possible probe of new physics that may happen. Here are, so let me say, chiral, diagonal, universal. Now we come to experimental tests, perhaps for the first time. So the decay rate into muon over the decay rate of the Z into electrons, experimentally known to fantastic accuracy of about 3 per mil, very much consistent with 1. Tau over E, almost similar accuracy, within 1 sigma, consistent with 1. Diagonality, off-diagonal Z decays have not been observed, they're only upper bound and they are very strong of the order of 10 to the branching ratio of 10 to the minus 6 or 10 to the minus 7, which means that out of 10 to the 6 or 10 to the 7 Z decays, not even once it decays in an off-diagonal way. And now the first demonstration that we can get this for the rho equal 1 relation. Said the left-hand side was mw squared over m z squared. From this we could deduce sinus squared theta, which was about 0.22 or 0.23. We can also now form interactions. So the ratio between the z decay rate into charged leptons and neutrinos depends on sinus squared theta. And from the experimental value, we get a value that is indeed consistent with the one that we got from the spectrum. And finally, there is a demonstration that parity is violated in the Z decays. So we can separate Z decaying to tau left minus tau left bar and tau right minus tau right bar. And so the decay rate into the left-handed minus the right-handed over them should be 0 if parity were conserved, and it's not. That's an experimental value. It can again be used to find sinus squared theta from a completely different set of measurement, and it's 0.23. Within errors and within the fact that there are corrections even in theory to that, it's again consistent. Okay, we are about to finish the interaction, so let me go on with that. Finally, the W interactions. This is how it appeared in the covariant derivative. And it leads, so T plus and T minus are raising and lowering operator. It connects the upper bound, the upper component of a doublet, of the fermion doublet, to the lower component. And this is what it gives. It gives ni E left bar times E left with this coefficient, ni mu left bar U left minus with this coefficient, and ni tau left bar tau left minus coupled to the W. These interactions are called charge current weak interactions. And unlike any of the other particles, posons that we've seen so far, the Higgs particle, the photon, and the Z, it couples to two different particles, a neutrino and a charged leptons. This should have been expected because the W is charged, and it could not have coupled to the same particle. Isn't consistent with U1 electromagnetism. So it's kind of a new type of interaction, changing. So charged lepton can emit a W and become a different particles. We did not see that so far. So this is how it looks. And again, the things that follow from the definition of the model, first of all, it's chiral. It couples only to left-handed fields. The right-hand, because the W plus minus come purely from the SU2 triplet, unlike the Z, which is a combination of the SU2 triplet and the B field, which is another field. And the right-handed fields are singlets of SU2, so they do not couple to the W. The fact that it's chiral immediately tells us that these interactions violate parity and charge conjugation. Still, the coefficient is real, so it's CP conserving. It's diagonal in the sense that each charged lepton couples only to one of the neutrinos, and each of the neutrinos couples only to one of the charged leptons. So it's ni E, E, ni mu, mu, ni tau, tau. So if you put a row vector of ni E, ni mu, ni tau, and a column vector of E, mu, and tau, then the coupling is diagonal and universal, the same entry on the diagonal to each of these. And some of the tests of that: universality, the decay rate of a W to a muon neutrino versus to electron neutrino should be 1, this ratio. It's 1. Tau in E should be 1, and within 1 sigma it's 1, so it's 1. We can also extract sinus squared theta from the interaction rates. Here it comes 0.215, close enough that, again, experimental and theoretical considerations make it consistent. This is deduced from the muon decay, and that would be the last comment that I make today. So there is something here called G Fermi, this combination of MW, W. So it's a measurement of this, the muon lifetime, and from that we can tell the value of the vacuum expectation value. So far it was just a parameter V, but it has a value in this parameter based on experimental measurements of 246 GeV. Now, last comment. Yesterday I was asked whether V runs, and I thought it doesn't. I didn't know to argue, so I wrote an email to my partner, Yuval, in this lecture. Does V run? And he answered, of course it runs. So, forget what I said yesterday. V runs, but the running of V is negligible. So that's why no one refers to it ever in the literature. It's a very small change along energy scales. So this number is there. It's mu squared over lambda. Both mu squared and lambda run in a calculable way, and this ratio run, but very little. So theoretically, yes, practically negligible. That's Yuval's answer, and I hope he's right, so that I don't have to regret what I say twice, but only once yesterday. So I'll stop here because it's 11:34. Yeah, we did not finish this chapter. There's a little more, but we'll do it in the afternoon. Yeah. Okay. A lot of stuff for an hour and a half. Yeah. Yes.
So can you go back to the slide where you talked about this vacuum expectation value of the Higgs and where you choose the T3 direction for the web?
Yes.
I think a little before that. Yeah,
Yes.
this one. Yeah, so like, do we really have a choice here? Like, if we choose it to be the upper component, like, wouldn't that mean that the vacuum itself is charged or something like that?
No, because there would still be one combination of generators under which the vacuum is invariant. And this combination, if it's the lower component, it's T3 plus Y. If it's the upper component, it's T3 minus Y.
Okay.
And so I will just change what I define as Q, in this case, from T3 plus Y to T3 minus Y. And
So one of them have to be zero.
one of them,
Like, both cannot be non-zero. That's
right, yes.
Yeah.
Either the upper component or the lower. And if you wonder, in this, for example, you may ask yourself, so I'll ask yourself, so what happened to the Yukawa terms if the vacuum expectation value is up there and not down? Would it give neutrino masses instead of the charged leptons, which I did the exercise here? So the answer is no, it would remain the same because the upper component,
you will change the components of the doublet.
yes, it
basically.
will change the charge of the component. So I will call them just the different names, yes.
So why again do we have to keep one of them zero? Like,
Why?
it's only one of these two possibilities, right? It cannot be like both of the components are non-zero, right?
I used to think that no, it has to be one of them, but I have to argue why. So either I'll answer later or I'll ask Yuval and give you the answer tomorrow. But
I suppose
it-
we can have both of them, but then this Q will have other components in the linear combination. So the basis, chosen basis is T1, T2, T3 is very special choice. We can have a very
So
weird
it's,
choice of T1, T2,
some
T3.
combination, if you choose
Yeah.
both of them, that also T1 and T2 will enter.
Right. It will
Okay,
enter
thank you,
in
yes.
the expression.
What T1 and T2 do is, in a sense, if you have in one component with a T1 acting on it, it gives you also the other component. And so if you put it in both, there will be a complicated combination of
Yes.
T1, T2, T3, and Y. So this is just simple. Thank you. Yes, absolutely right. But there would still be one combination that is involved, but it's much more complicated to find.
Yeah, just add to that, like I read somewhere that if you write the Higgs doublet, you would have the first component as phi plus and the second component phi naught. So if the phi plus component gets a vacuum expectation value, that would mean that empty space is charged.
Okay, so
That's
the fact that you call them the upper component phi, let's do it again. So I have phi, which is phi T3 equals plus half, and phi of T3 equals minus a half, and Y is plus half. So if Q is T3 plus Y, then this becomes phi plus and phi 0, where this plus and 0 are Q, stand for Q. Right, T3 plus half, Y plus half, then this T3 plus Y equals plus 1, and T3 minus a half, Y plus half, then this becomes 0. The name phi plus and phi 0 would not hold if Q were T3 minus Y,
Every phi 0 and phi
then
minus.
this will become phi 0. You gave, so in correspondence to the fact that you gave the vacuum expectation value here, and this will become minus. So what are the charges depend on what is the conserved charge, the one that is not broken, and that depends on where you put the vacuum expectation value. But I think from this you can start sensing that the definition is in such a way that in the end it's all the same picture. So you do not, the physics is the same whether you put it upstairs or downstairs or whatever. What is charged under the remaining symmetries, what is not, is changing, but I give them now the corresponding names as appropriate.
Sir, can the leptonic standard model explain us why there are no cross-generational decays in the weak interaction?
Why there are no?
Cross-generational decays in the weak interaction. Like why can't we go from electron to muon?
Yeah, so it does. It's a little bit more detailed. So for the photon, it's clear why it doesn't couple different generations to each other. I hope I understood your question.
Right.
Yeah. The Z, it's more complicated. I say it's not a gauge boson of a conserved symmetry. So it has to do with a special property of the standard model. It's written here. I did not explain it. It will take 5 minutes or so to explain. But it's a special feature of the standard model that all fermions that have the same chirality and the same charge come from the same SU2 cross U1 representation. This is not necessarily the case. Remember that Q equals T3 plus Y, and this, let's say the charged lepton have minus minute. Okay, so something here confuses me, but so all the left-handed charged leptons have T3 the same and Y the same. They all come from the two minus a half, all left-handed ones. The charged leptons come from 2 and minus half. Okay, my confusion is over, it's just tiredness. So they all have T3 equals minus a half and Y equals minus a half, which gives a charge of minus 1. You could think of a model where you have left-handed fermions that are, so this is with 2 minus a half. It comes from a singlet of SU2 with hypercharge minus 1, and in that case these fields will have T3 equals 0 because it's a singlet, hypercharge minus 1 equals minus 1. If you would have in the model such left-handed fields, the Z couplings would stop being universal. There would be off-diagonal couplings, there would be different couplings to the different generations. It's not so difficult to prove that if all of them come from the same T3 and Y, then it's okay, then it's universal, not okay, it's universal, and that's the case in the standard model. While if they come from different representations, SU2 cross U1, or in particular different T3 and the same Q, then the coupling of the Z in that sector would be including non-universality and non-diagonality. For the W, why the W couples universally to these pairs, it has to do with the fact that in this model, the neutrinos are degenerate. Again, it's a little bit complicated, but in the extensions of the standard model that account for the fact that the neutrinos are not degenerate, because that's what experiments tell us, in all of these, the Z does not couple universally, the W does not couple universally, similar to what is happening in the quark sector. In the quark sector, we'll see in the standard model, it does not couple universally. So once you allow for neutrino masses that are different from each other, this will also apply in the W interactions. So there will be what's called a mixing matrix, which will, so it has to do with the fact that neutrinos are degenerate. And okay, let me say 2 more words to those that can understand this. So the fact that neutrinos are degenerate means that so first of all, so the neutrinos mass eigenstate have mass 0. Any rotation among the 3 massless neutrinos is still a mass basis for the neutrinos, because they have the same mass. It doesn't matter very much for this that they are massless, but just that they are degenerate. Once they are degenerate, and so it means that in the basis that I chose, where the charged leptons are mass eigenstates, then their partners in the doublet, the ni, ni, mu, ni, tau, which are defined by being the partners in the doublet of the mass eigenstate, ni, ni, mu, ni, tau are also mass eigenstates. They have well-defined masses, 0. And so it's an interaction basis. Everything there has well-defined transformation properties under SU2 cross U1. These are still the doublets of SU2 with hypercharge minus half, but it's also mass basis for both charged leptons and neutrinos. If the mass basis is also an interaction basis, it means that the W couplings would be universal. Once neutrinos become massive, there is no interaction basis that is also a mass basis, and then universality goes. For those of you that this was too complicated, I apologize, but that's the explanation in this model. So it's different. The W is the degeneracy, the Z has to do with the coupling. There is also a question of why the Higgs coupling are diagonal. It's also a special feature of the standard model. In extensions, it could be off-diagonal couplings as well.
Any other offline question? So there's something online. Devabrata Sahu is asking, why don't we see this charged scalar?
Why?
Don't we see this charged scalar?
Yeah, so we have two charged vector bosons, the W plus and W minus, and they become massive as a result of the spontaneous symmetry breaking. So they must get from somewhere an extra degree of freedom, because now they have 3 degrees of freedom. And the two components of the charged scalars, this phi plus that was here, so the two components of the charge are eaten by the two charged vector boson. The imaginary part of this phi 0 is eaten by the Z boson, and the 1 degree of freedom that is not becoming a longitudinal component of a massive vector boson is the Higgs boson. So that's what happens to these 4 components. 2 are eaten by the W's, 1 is eaten by the Z, and 1 is a physical scalar particle.
Okay. So no more questions? Okay, so let's thank you. See you again.